nothing with that. Okay. Sorry, I lost control of my mouse for a second. I think we've got it now. All right, so how's everybody doing this morning, or afternoon, I guess? Can you hear me? Let's start with that.
Yeah, not doing too bad.
Okay. Okay. So obviously I'm in a slightly different location today. I'm down in the materials lab, because that's where I was this morning, so I was already set up here. So we are going to be working on equations of motion today. So you should have a handout. So if you go to the files and then class materials, lecture handouts, this equations of motion document is what you want. So go ahead and if you can get that printed, and we'll be making use of that. So I guess that's what we go with. All right, so this is what that handout looks like. The top of it should look familiar because it's what we started doing last time. So our goal at this point is we're really getting into the dynamics portion now. So we've been mostly focused on kinematics, which is motion in terms of position, velocity, and acceleration. Okay, and we saw that acceleration could get pretty complicated depending on how many reference frames we were dealing with, what types of reference frames we were dealing with. I'm going to go ahead and start recording this. But up to this point, we've mostly looked at motion in terms of kinematics. And so we haven't really worried about the forces involved. So functionally, we're a couple of weeks behind where we should be right now, but we're going to try and get through as much as we can. So we're looking at, we're starting with dynamics or kinetics, which essentially means applying Newton's second law to motion. So as we're working through this, we're going to be looking at kind of three different types of setups. So we'll look at particle motion as a result of forces. And so we've got sum of forces in all directions are equal to the mass times the total acceleration. We can break that into X and Y because X and Y have independent, or we treat them as independent. Forces in X only cause accelerations in the X directions. Forces in Y only cause acceleration in the Y direction. And then for our systems of particles, we're looking at kind of multiple things that are all moving in a system. And our system might be many particles like this, or it might be, 2 or 3 that we're looking at and considering to be a system. So when we get to collisions, we'll be doing a lot of looking at systems of particles, which might mean 2. And so here we've got external forces and internal forces, and we'll get into a little more detail about what we mean by those. But essentially, external forces are going to be forces coming from outside of our system. So if each of these particles is part of our system, what would be some forces that would be external to that system? This is going to be very dull if none of you respond.
I'm kind of confused on what you're asking specifically. What do you mean?
Sure. So the idea here is that, okay, let's maybe make this a little smaller system. And actually, I'm going to change something here real quick. Make this. Okay. That's probably going to be better. Okay, so let's think of it in terms of maybe 2 cars. So if you have 2 cars and they collide, what forces in that collision would be internal to the system, and what might be external to the system? So I'll give you an example of one. The weight of each particle, or the force of gravity, would be an external force. 2 particles colliding with each other would have an internal force between them. So forces that are internal to the system have an equal and opposite pair that's also in the system. Other thoughts or ideas?
Is friction external?
Friction would be an external force. Mm-hmm.
Okay.
Okay. All right, we'll get to a little bit more with that in a bit. Then the other type of system we'll look at is a rigid body. So if we have something that has shape and dimension to it, if we apply forces to it, and maybe a concentrated moment, we're going to end up with kind of a combination of rotation and translation. And there may be a point, so we're going to call this point here at the origin of the attached reference frame, point P. And we may have another location that's really the center of gravity that we'll call G. So systems of particles are also going to have a location that's their center of gravity, and so we use a symbol like this. So it's essentially a circle with kind of 2 of the quarters filled in. And so that's going to be the center of gravity of the whole system. And so we'll have a radius to that, and the acceleration of the whole system will be calculated as the acceleration of that location. Okay, so this is kind of the overview of systems we'll look at. Are there questions right away? Okay. So we'll start with rectilinear translation, just like we did with kinematics. And so rectilinear translation, again, is moving in straight lines. We're not changing orientation because we're just translating. So there's no rotation. There's just translation here. And so as we work through that, we have, or we're always going to start with Newton's second law. So sum of forces is equal to mass times acceleration. And we can break that down into directions. So we can say the sum of forces in the x direction, I hat, plus the sum of forces in the y direction, j hat, plus sum of forces in the z direction, k hat, need to be equal to the mass times our acceleration vector. So ax I hat plus ay j hat plus az k hat. Okay, and then we can again look at the three systems that we talked about. So for particles, we have just sum of forces in the x direction equal to m ax, sum of forces in y, m ay, and sum of forces in z equal to m az. Okay. And when we go between particles and systems of particles, we're essentially saying that for each particle in our system, this will be true. So the same thing that's true of particles will be true for each particle within a system. And so we talk about the ith particle. So not a specific, one specific one, but we're keeping it general which one we're talking about. And we'll have some internal forces acting on each particle, and we'll have some external forces acting on each particle, and that will give us the mass times acceleration of each individual particle. So when we get to the system level, we need to add all of those up. And so we'll add up all of the internal forces plus all of the external forces, and we can come up with a sum of the mass times acceleration of all of the particles that make up the system. And so it turns out that because our internal forces are internal to the system, when you've got one particle acting on another particle in the same system, they're both exerting equal and opposite forces on one another. So for every internal force, there's an equal and opposite pair that's going to basically cancel it out when we sum. And so we end up with the sum of our external forces being equal to the mass of the whole system times the acceleration of the center of gravity of the system. Okay, and so if we were to look at some individual particles, we'd have a sum of internal forces external forces and internal forces. And together they would give us the kinetic diagram, or the total mass and acceleration, or the acceleration dependent on the particle mass for that particle. Okay, and then when we get to rigid body movement, for rectilinear translation, we have sum of forces in x equal to the mass times the x direction acceleration of the center of gravity. Sum of forces in y, m times the y component of the center of gravity acceleration. And then since we're dealing with translation and not rotation, the sum of moments about our center of gravity will be 0. Okay, so we've got particles, we've got systems of particles that are essentially adding up a whole bunch of particles into one general system. And then if we take all of those particles and we make them kind of one rigid object that's moving in a plane, and I'll point out this is planar rigid body motion, we're sticking with 2D for the rigid body motion, then we're going to be interested in acceleration of the center of gravity, just like we were with systems of particles. But now we're going to consider moments. And we didn't consider moments with particles or systems of particles because there isn't really anywhere to apply a moment arm or to have a moment arm with a rigid or with a particle. So that only really comes into play with our rigid body motion. But because we're not because we're translating and not rotating, our sum of moments needs to be 0. Okay, any questions at this point? Doing okay?
Yep.
All right. All right, so then we can take a look at the curvilinear translation on the next page. So we've talked about this before, but essentially with curvilinear translation, we're looking at following a path that may or may not be a straight line. There may be all sorts of curves to it. And so we're following that path, but we're not changing our orientation. And so we said before that this is kind of like the carts on a Ferris wheel. So as you're going around the Ferris wheel, you're following a circular path, but you aren't actually changing orientation. The car stays vertical the whole time. And so we'll talk mostly with just the normal and tangential directions here. So there's a few things I've noticed as I'm grading exam 2. So when we're dealing with curvilinear translation and the normal and tangential units, we're going to need to have, so we need to keep track of which directions are which. So our normal direction is always going to be perpendicular to our path. So toward some sort of a center of rotation. We might, and depending on how we write it, we might call this rho for the curvature, or we might just go with some version of r for that radius. And so that's going to depend on how we're oriented. If we're in, so this would be kind of a 2D motion, you'd have a tangential direction then that would be tangential to the path. Same thing over here. We can have a tangential direction. And then I'm actually putting our center of curvature and our normal direction that way, and then giving us a third dimension that we're calling B. Okay, and so with this, we can have forces in any of those directions. So we could have forces in our tangential direction. So we'll have a sum of tangential forces in that tangential direction, and I'm using lambda. I think the book maybe uses E as the direction marker. Could have a sum of forces in the B direction, and also a sum of forces in the N direction. And so here, if we sum our forces and set them equal to mass times acceleration, that means summing forces in the tangential direction will give us mass times acceleration in the tangential direction. Sum of forces in the normal direction gives mass times acceleration in the normal direction. And same thing with B. Okay, and then as a reminder, this tangential direction acceleration is the derivative of velocity with respect to time. So tangential acceleration a sub t is going to change our tangential velocity. A sub t, if we're dealing with circular motion or something like that, is going to be equal to r times alpha, which is the angular acceleration. And then a sub n is our normal direction acceleration, or perpendicular direction acceleration. If we're in polar coordinates or something like that, we call it the centripetal acceleration or the radial acceleration. And that's v squared over rho or v squared over r, depending on how we've defined the radius of that curve. Okay, and then with rigid bodies for curvilinear translation, we have a sum of forces in our normal direction, gives us mass times the acceleration of the center of gravity in the normal direction. Sum of forces in the tangential direction gives mass times acceleration of the center of gravity in the tangential direction. and sum of moments about the center of gravity are still 0 because we're still translating. Okay, questions at this point? Okay. Hearing none, we'll move on. So we have an example. We have a 10 kilogram projectile being fired vertically from the ground with an initial velocity of 50 meters per second, and we want to determine the maximum height to which it will travel. Okay, so what do we know?
We know the mass and we know the initial velocity.
Okay, so we have mass is equal to 10 kilograms. We have a velocity that's 50 meters per second. Do we know anything else about that velocity?
It's straight upward.
Okay, it's straight upward, so it's just j hat. So we don't need to worry about what angle it's fired at. It's just straight up, so everything is in the y direction. Okay, so what would our free body diagram look like after the projectile is fired? What's acting on our projectile if we're going to start by ignoring air resistance? We're just going to have weight of the object, so just gravity at this point. We're not going to draw velocity on to the free body diagram. We only put forces on our free body diagram. So we've got our weight, and we know sum of forces in the y direction give us mass times acceleration in the y direction. We've just got weight, and so we'll have a y equal to g, or negative 9.81 meters per second squared. Okay, and so at this point we can go back to our kinematics and use our kinematic equations to solve. So our weight is going to be constant. We're ignoring air resistance, which means we have a constant acceleration. And so we can use one of our kinematic equations that is fairly straightforward. When we've got constant acceleration. So what do you think we should use for which of our kinematic equations should we use here? Going back to the very basics. which of those equations looks the most useful to what we know? Okay, that third one. What do we know about that third one?
Wouldn't we want to use the top one because we know our initial accelerate or velocity, and we know our acceleration, and we could just solve for when velocity equals 0 because that's a turnaround point.
Okay, so we know the velocity is going to be equal to 0. So the velocity at maximum height is 0. Okay, so what would we be solving for with that first one? So there's two ways we could go about this. We could use this first one, and we know the two velocities, we know our acceleration, and so we could solve for time that we could then put into the second one. Or we can skip that altogether and just go with this third one because we know the two velocities and we know our acceleration, and so we can solve right away for that change in height. Okay, so that's what I'm going to go with. So if we do v squared minus v naught squared, that's going to be equal to 2a delta s, which means delta s is v squared minus v naught squared over 2 times a. We said our final velocity is 0 meters per second. We're subtracting our initial velocity, which is 50, and then dividing by 2 times negative 9.81 meters per second squared. And so if we do that, we're going to come up with 127.42 meters. And so our maximum height will be 127 meters. Okay, so we could use the other two, and that's fine. This one just gets us to an answer a little more quickly. Okay, so this should be something very similar to what you did in physics. And so now we're going to not neglect air resistance and take a look at what happens when we consider air resistance. Okay, so we've got the same list of knowns. So we know we've got a mass of 10 kilograms. We've got V naught equal to 50 meters per second. We've got a final velocity of 0. But now we've also got a force, or a drag force, that's equal to 0.01 times our velocity squared. Okay, so now we've got a little bit of a different situation. Okay, so if we draw our free body diagram, we've got our weight, and at this point we've sent our projectile upward. So how is drag going to be acting here? What direction will drag be acting?
It's going to be opposite of motion, right?
Yep, so it's going to be opposite of motion, so it's actually going to be pointed down while we're going up. Okay, so drag like friction are going to oppose motion. And so we've actually got two forces that are going to be working together to slow down our projectile. So do we think we're going to go higher or lower with drag? Okay, so we're expecting our height to be lower. Good. All right, so now if we sum our forces, we have weight, and we have our force of drag, and that's going to be equal to our mass times our acceleration. And so I'm going to actually go ahead and substitute a couple of things in here. So for our weight, we know that's 10, we've got 10 kilograms and we need to multiply by g. So that'll be negative 98.1 newtons. And then our force of drag, we said, is 0.01 times the velocity squared. That's equal to 10 kilograms times our vertical acceleration. And so if we solve for a y, that's going to be negative 9.81 minus 0.001 v squared meters per second squared. Okay. So this is looking a little bit funky. But if you remember from early on in our kinematics discussion, we said we could take a dy and set it equal to v dv. And so if we rearrange this, we have dy is equal to v over a dv. And so that's what we're going to use to work through this. Okay, so we're going to go ahead and integrate this equation. So we're looking for our change in height. So we want to integrate dy from 0 to h, and then integrate our other side. So we've got a dv, so we can go from v naught to vf. And then we have velocity divided by our acceleration, which we said was here. So we've got negative 0.001 v squared minus 9.81, and we're integrating that with respect to dv. Okay, so left side's pretty easy. We have y evaluated from 0 to h. I'm going to go ahead and take the negative sign that's in the denominator here and pull it out of the integral. We're integrating from 50 meters per second to 0 meters per second. Zoom in a little here. Okay, and so then what we've got on the inside is v 0.001 v squared plus 9.81. Okay, and this 0.001 is a little bit annoying to deal with, so I'm going to just multiply top and bottom by 1,000 a piece. And so now we've got the negative integral from 50 to 0 of 1,000 v divided by v squared plus 9,810. All right, so this is still a little bit annoying to deal with, but we'll use a u substitution. And so let's say u is going to be equal to our denominator. So v squared plus 9,810. So if we take a derivative of that, so du, we get 2 times our velocity times the derivative of velocity. And so that's going to simplify our integral. So we now have h equal to the integral let's see, we'll go ahead and ignore what our limits are for now, because they'll have changed. But now on the denominator, we have just u. At the top, we said du is equal to 2 times v. So we really, in the top now, have 500. And we're integrating with respect to du. And so that's going to give us, we can take the 500 out of the integral, integrate from u naught to u, 1 over u du. And so that'll give us 500 ln natural log of u evaluated from u naught to u. And so if we substitute back, we have h is equal to negative 500 times the natural log v squared plus 9810 evaluated from 50 to 0. And so we can put in the values that we had, and this should work out to be a height of 114 meters. Okay, so if we ignored drag, we got to 127 meters. With drag, we're getting to 114 meters. It's not a ton less, but still fairly substantial. Okay. Are there any questions on this one? Are you still writing? Anything else you need to see? Okay. So I think we've got another example. So now we've got a 3 kilogram disc that is attached to the end of a cord. So here's our disc D. And so the cord is attached at one end to our disc and at the other end to a ball and socket joint, so it can, whoops, you can't actually see that. Okay, here we go. So here's our disc. It's attached to a cord. At one end, the cord at the other end is attached to a ball and socket joint. So it's essentially free to rotate anyway without twisting around. So it's not going to wrap up on a post in the middle. It's just going to keep freely rotating. And so it's going to be dropped onto this platform that's rotating. And we're not told how fast it's rotating, we're just told it's rotating rapidly. And so we're going to drop the disc on, release it from rest, and then wait for friction essentially between the disc and the platform to kind of carry it to the point where we reach a point where the cord will break. Okay. So let's start with what we know. Okay, so we know we've got a disc with a mass of 3 kilograms. We know we've got a length of cord or a radius that's 1 meter. We know that our friction, kinetic friction, is 0.1. Has a coefficient of 0.1. And we know that the maximum tension in our cord is 100 newtons. And we're trying to find the change in time until we get to a point where the cord breaks. Okay. So this is one that we probably want to start with a free body diagram of our disc. So here's our disc D. And so we're going to have our normal direction. We'll have a tangential direction and then a perpendicular or a kind of an out of the plane direction. And so where do we have forces that are acting on D? This is the class participation portion of the day.
Can you re-explain what the B direction is? Like, I get that the N is normal and T is tangential or whatever, but I don't know what B means.
So it's essentially it's our third dimension. I don't know that it actually has a name associated with it other than to say that here, so where our disc is drawn, our tangential direction is going to be tangent to that circle. Our normal direction is here. And then this one's kind of perpendicular to the platform. So it's just going to be our third dimension. but it's the vertical one here, which is the key.
So do we start this problem by like using a tangential acceleration and then somehow plugging that into our kinematics equations and probably doing an integral?
We'll get there, but we're going to do a free body diagram first.
Oh, okay.
So what's the force we can add to our free body diagram?
There's
Friction.
tension.
Okay, so we've got friction and tension. So where should tension go?
In the normal direction towards the middle.
Okay, so normal direction away from the disk. We'll have our tension. Where should friction go?
In our tangential direction in the opposite of rotation, right?
Okay, so it's going to be, yep, so somehow
Negative.
opposite of rotation. Yeah, so if our platform's rotating this way, it's going to, so the piece here that we have to kind of keep track of is where things are moving and how forces are acting. So the platform, if there's friction between the disk and the platform, it's actually going to tend to carry the disk with it, because relative to, so it depends on where our relative motion is, but essentially it's the friction that's going to get our disk moving with the platform. So in this case, friction is actually going to be in the same direction that the disk is moving. So it's a little bit, it feels a little bit backwards, but essentially we've got our disk and we've got the platform. And so if our platform is moving this way, the friction acting on the platform is the opposite. So the friction is going to resist the movement of the platform, but that means that an equal and opposite force is being exerted on the disk. And so our friction is actually in the direction that the platform is moving. Does that make sense?
Yeah, that makes sense.
Okay. Okay, what forces are we missing? Anytime we have friction, we need what?
Acceleration.
We're not there yet.
Ah,
We're missing two forces.
there's weight.
Normal force.
Normal
Okay,
force.
weight and normal force. So anytime we've got friction, we need a normal force. And we've also got our weight. Okay, good. So now we can sum forces. And so if we sum forces in the B direction, we've got our normal force minus our weight should be equal to what? What are my options when I sum forces? They can either be equal to mass times acceleration, or they can be equal to 0.
Is it 0?
Why should it be one or the other here?
Because it's not moving up or down. It's just moving in the
Okay.
horizontal.
Yep, so we aren't moving up or down, so we're not going to worry about acceleration in the B direction. So it's going to be just 0. Okay, so that tells us that our normal force in the D direction is equal to our weight, or mass times gravity. And so that's 3 kilograms times 9.81 meters per second squared. And so our normal force will be equal to 29.43 newtons. Okay, so now we can sum forces in our other directions. So if we sum forces in our tangential direction, we do want to end up with a sub t. The only force in our tangential direction is friction. And so that's going to be, so we've got kinetic friction, right? So we can actually, we know what the value has to be. If we had static friction, remember static friction can scale. And so depending on what we had, or depending on where things were at, we might have scaling values, but since this is a kinetic friction, we know it has to be mu sub k times nd equal to our mass times acceleration. So our coefficient of friction was 0.1 times nd, and that'll be mass times tangential acceleration. Okay, or putting this a slightly different way, we know nd is equal to our weight, which is mass times gravity. And so that's going to be 0.1 mass times gravity is equal to mass times tangential acceleration. Our masses cancel, and our tangential acceleration is 0.981 meters per second squared. Okay, so this is the acceleration we're going to get from friction. Okay, we can also sum our forces in the normal direction. And that'll give us mass times normal direction acceleration. The only force in that normal direction is our tension. What was our normal direction acceleration equal to? Do you remember? How do we get normal acceleration?
Do we have to somehow find a velocity or something?
We don't necessarily need to find it, but what's the formula?
Velocity divided by radius.
Close.
Velocity squared divided by radius.
There we go. Okay, so velocity squared divided by radius. All right, so that means that our tension is equal to mass times velocity squared divided by our radius. We know mass and we know radius, so that's 3 kilograms times velocity squared over 1 meter, or 3 v squared. Okay, so this is going to change depending on, so our tension will be changing as we gain velocity due to our tangential acceleration that's coming from friction. Okay, so we also said that our maximum tension is 100 newtons. And so we can come up with a critical velocity. So I'm going to use subscript CR here for critical velocity. And so if we solve for that, we'd need to take our tension divided by 3 and then take a square root. So we're going to do square root of T max over 3. And so we'll come up with our critical velocity will be 5.77 meters per second. Okay, so now we know some other things. So we know that our initial velocity is 0 because we said we're starting from rest. Our final velocity will have to be our critical velocity because that's the point at which our cord won't hold anymore. And so that's the 5.77 meters per second. The acceleration to get us there is our tangential acceleration. And so now we can solve for time. Okay, and we can use that first kinematic equation. That was V final equal to V initial plus acceleration times time. And so if we solve this for time, we've got V final minus V initial divided by acceleration gives us our change in time. And so that's 5.77 meters per second minus 0 and divided by 0.981. And so we should come up with our time for the cord to break is 5.89 seconds. Okay, so again, we started out here with our free body diagram. We knew a few things. So we knew we had to have weight and a normal force that would give us tension. We figured out that would give us friction. We determined that the friction is actually moving in the same direction as the platform is moving because it's going to be the friction from the disc on the platform will oppose the motion of the platform. And so the friction force on the disc has to be equal and opposite to that because it's going to be kind of picking up that disc and carrying it along with it. And so we solved for what that normal force had to be equal to so that we could come up with a friction force that was going to give us our acceleration in the tangential direction that would be changing our speed. We came up with that value. Then we used normal direction and the forces there to figure out what with normal acceleration, as we're picking up speed, what the tension has to be to keep that disc moving in a circle. We came up with, or we knew what our maximum tension was, and so we could come up with a critical velocity that would be the maximum velocity we could get to before our tension hit its maximum. And then we applied kinematics with that information to come up with the time it took to get to that velocity. Okay. How are we doing? Still hanging in there?
Sure am.
All right. Any questions on this one? Okay. So we'll go ahead and take a little closer look at our systems of particles. Okay, so this is similar to the drawing we had before. We've got our center of gravity of the system and some sort of a R sub G vector, position vector of that center of gravity. We have an internal coordinate system. That we're working with, and so we've got some point where we're measuring everything from location, directions of things, all of that. On each individual particle, we can call this the ith particle. There are internal forces and external forces that are acting on it. And so, as usual, we apply Newton's second law. And so for each particle, we can sum the external forces and the internal forces and find out how that particle will accelerate. And so the capital F forces are our external forces. And so this is going to be things like are listed there. So gravitation, electrical forces, magnetic forces, and then contact between the particle and anything that's outside of the system. Okay, so if we had a system that was contained in a box, the sides of the box might be exerting external forces on particles bouncing around inside of the box. But those would be considered external forces because they're acting on the system rather than within the system. The lowercase f are our internal forces. And so this is forces that are happening inside the system as particles run into each other, parts of the system run into each other. They exert contact forces or normal forces on one another. And so those get counted as internal to the system. Okay, so then for our system, we can sum up all of the external forces and all of the internal forces. And the total sum there should be equal to the sum of all of the masses and accelerations of the individual particles. Okay, and so the little i's are all the same, and they're meaning individual particles within the system. And then G, like I said, is our center of mass, or center of gravity for the system. Okay, and like we had before, we have external and internal forces acting on each particle, and that'll give us some sort of a mass and acceleration of each particle. Okay, and like we talked about on a previous page, we sum up all of the external forces on the system, we get the net motion of the system. The mass times acceleration of the center of gravity of the system is equal to the sum of all of the masses and their accelerations within the system. And so essentially, if we sum up all of the external forces on the system, we should be able to calculate how the center of gravity of the system is accelerating. Okay, and then just to clarify those internal forces a little bit, the forces that are internal to our system are going to cause acceleration of the individual particles, so they'll contribute to acceleration of individual particles. If you think about two particles bouncing off of each other, that contact is going to cause acceleration of each of those. But within our system, if particle A and particle B collide, particle A exerts a force on particle B and causes B to accelerate, but B is also going to cause a force on particle A and cause A to accelerate. So we end up with this equal and opposite force causing acceleration of some other particle. And so our internal forces will cause motion of specific or of individual particles within the system, but they're not going to contribute to acceleration of the overall system. Okay, so the overall system is only going to be moving based on external forces.
Can you give an example of a internal force? Like I'm trying to understand, like what would that be in a common day scenario?
Mm-hmm. Yeah, so this is not necessarily what we're thinking about here, but if you think about like an Olympic diver, for instance, and you think about all of their limbs and body segments as kind of particles within the system, they can move their arms, their legs, they can do flips, so they can cause acceleration of parts of their system with forces, muscle forces acting on their arm are going to cause their arm to move. But that's not actually going to change the trajectory of their center of mass. Does that make sense?
Yeah, okay. Thank you.
Okay. Okay. So that's our little more detail with systems of particles. So we'll look at a little more detail of rigid body motion. And so with this rigid body, we're going to call the origin of the attached reference frame P. The rigid body will also have a center of gravity. And so that's where we'll apply its weight. We may also have other forces being applied to it. There may also be like a couple moment being applied. And so we can have, Oh, sorry. I said what?
It looks like she accidentally unmuted.
Okay. Okay. All right, so we can have all sorts of things being applied to the rigid body. We're going to sum forces. The forces are going to tell us how the center of gravity is going to accelerate. And we can break that down into X and Y components. So this is something we've done before. So that should be pretty much old hat at this point. Now, when we allow for rotation and not just translation, that means that our sum of moments about the center of gravity is not going to be 0. And so instead of being 0, we're going to have the sum of moments about the center of gravity equal to our moment of inertia about the center of gravity times our angular acceleration. Okay, and so to write that out a little more, or in a little more detail, we've essentially got R crossed with F for the moment, and then on the other side, it's really R cross MA. And so this gets a little more complicated looking. Functionally, this acceleration can be treated as a tangential type of acceleration, and so we can divide by r to get to alpha. But then we've got another r, and so it's r squared times m, which is our moment of inertia. So that's how this functionally ends up working. Okay. So a lot of times we're going to want to find moments about a point that isn't the center of gravity, either because we don't, we'd have to calculate where that is, or just generally we don't necessarily need to know acceleration about the center of gravity, and so we're more interested in our other point P. And so if we do that, we need to apply rotation about, or some of our rotation acceleration formulas that we've talked about previously. And so we've taken our acceleration and broken it down into acceleration of point P, the angular acceleration of the object crossed with r. So essentially that r, and then omega squared minus r. So a normal direction, a tangential direction, and then a translation. Okay, so if we rearrange this a little bit, I'm going to distribute this r cross to each of those pieces. And so we have m sub I, and then r crossed with the acceleration of our reference frame, linear acceleration of the reference frame, plus r crossed with alpha crossed with r. And then we have omega squared and r crossed with r. Okay, do we see anything there we can simplify? Do we see anything there we can simplify?
looks like we can take an R out of the two parentheses, I think.
So we just put that in. So it was here. It was outside the parentheses, and then we put it into the parentheses.
Oh.
So what can we simplify here?
We can just make that internal parentheses R squared.
We have a
It's-
cross product.
Isn't R cross R just 0?
Yes. So anytime, remember when we're doing a cross product, we are multiplying perpendicular components together. R cross R is all parallel, so it goes away and is equal to 0. Okay, so we got rid of our last term. Then this next line is taking what we have here and expanding it. So we're replacing R with X and Y, and then replacing our accelerations with their components. So AX and AY, and that's all the way through here. Alpha is going to be, we're rotating in the XY plane, so alpha is in the K-hat direction. And we did that so that we can work through our cross products here. Okay, so if we start to do that, we have M sub I on the outside. Then we have X in the I hat direction. We could multiply by the X component of AP. What does that get us? X times X, X crossed with X gives us
0.
0. Okay, so that we don't get anything from that. So do X times AY. And what direction should that end up being? I crossed with J.
Positive K.
Okay. So we get a positive K hat. All right, and I'm gonna, well, let's see. AP sub Y. Okay, so now we've got Y crossed with AX. So that should give us something. We have J crossed with I, which should give us a negative K hat. And then Y times Y is going to be a 0 again. Okay, then over here, we've got two cross products. So I'm going to do that off to the side over here. So we have alpha times X. And that's K hat crossed with I hat, which should give us a J hat. We have alpha times Y. And that's K hat cross J hat, which will be negative I hat. And then we're multiplying again by this X and Y. And so we have X times X alpha J hat. We have an I hat and a J hat, so we can multiply those. So we get X squared alpha, I hat crossed with J hat gives us K hat. Then we have Y times Y alpha. So we get Y squared alpha. We have J hat crossed with I hat, which should give us negative K hat. But we've got a negative sign here. And so we get a positive k hat. So we can put that back over here. So we have alpha x squared plus alpha y squared. Okay. And so we can simplify this a little bit further and say m sub I times negative y acceleration of point P in the x direction plus x times a sub P in the y direction plus alpha r squared, and this will be in the k hat direction, which we can also just write as a counterclockwise arrow. Okay, so functionally this is for one point within, or one kind of particle within our object. If we want to get the whole object, we actually need to sum up all of those points, because each one is going to have an individual x and y location relative to the rest of the system. So if we sum up that, we've got, we're essentially going to be integrating this across all of the x and y locations, or across the whole mass. And so if we do an integral over the mass, we have y dm apx. So our y position is going to change depending on where we're at. AP is a constant relative to that, because everything is accelerating together. Then we get the integral over m x dm apy. And then for this last one, integral of r squared with respect to the mass times alpha. And we like when we get things into this form, because the integral of y over the mass is just the center of mass in the y direction. So it's just y bar times m. Yeah, y bar times m. So it's the first moment. We've got another first moment here. So x dm, integral of x dm, gives us x bar times m. And then integral of r squared with respect to the mass is a moment of inertia. And so for the whole system, we can say that the sum of the moments at point P, if we sum up all of them from all of the points, we end up with essentially a parallel axis theorem type of an equation. So we've got, where is our center of mass from the point that we're summing, multiplied by our distance, or by the mass and the acceleration of the location we're summing at, and then moment of inertia about that point and alpha. Okay, questions at this point? we can move on. Okay, so we're going to look at rotation about a fixed axis. So if we have rotation about a fixed axis, we can sum forces in the normal direction, and we have mass times our acceleration of the center of gravity in the normal direction, and that will have to be equal to m omega squared times r to the center of gravity. If we sum in the tangential direction, we get mass times acceleration of the center of gravity in the tangential direction, or m alpha times r. And then if we sum moments about the axis we're rotating about, we have moment of inertia about that point times alpha. Okay, so we can simplify that equation if we know that we're rotating about a fixed axis. Because we don't have to worry about that point translating in addition to the rotational motion we see. Okay. I'm going to skip the general plane motion because it's what we've already written down a couple of times. So it's the equation that we landed with here, and here, and here. And we'll take a quick look at rolling. So if we have a rolling motion, we have a cylinder that's rolling. Our center of gravity will be there in the middle. At ground, there's some sort of a force that's pulling forward. We've got a radius. And so if we do a free body diagram, we have our weight that acts at the center of gravity. We've got this force P that's pulling us forward. There'll be a normal force at the ground, and then some sort of a friction force. And that friction force will depend on how we're moving. And so if we sum forces in the x direction, we have sum of forces in the x direction equal to mass times acceleration of the center of gravity. So here that's P minus friction equal to mass times the acceleration of the center of gravity. If we're rolling, we probably are not traveling in a vertical direction, which means sum of forces in y, ag in the y direction. So we have normal force minus mass times acceleration due to gravity need to be equal to 0. Which is why I took the x off of the a sub g above. And then if we sum moments about the center of gravity, that's equal to I sub g times alpha. Functionally here, if we're summing moments about the center of gravity, normal force points through it. weight and P act at it. And so the moment is coming from our friction force times the radius will be equal to IG times alpha. Okay, so functionally we've got an equation here, an equation here, and an equation here. So we've got 3 equations, but we've got 4 unknowns potentially. So we don't know friction necessarily. We don't necessarily know our normal force. We've got alpha and A sub G. And so in order to get to another equation, we can use, we use 2 different conditions. So we need to know whether or not we're rolling with slipping or not. So if there's no slip, then our friction force is preventing slipping. We have a static friction. We don't necessarily know what that value is, but we do know that the acceleration due to gravity, or sorry, acceleration of the center of gravity here is going to have to be equal to alpha times r. Okay, so if we're slipping and there's actually a velocity here at the contact point, the acceleration at the center of gravity won't be equal to alpha times r. But if there's no slipping and this point has a velocity of 0, we have an instantaneous center, then the acceleration of the center of gravity has to be alpha times r. Otherwise, if we have slipping, we can use our friction equation. So if it's slipping, we know it has to be kinetic friction. And so we use mu sub k times n to get our other equation. Okay. Questions at this point? Okay, if you can, I'd like you to take a look at the problem here at the back. We won't have time to get through it all the way, but there are a couple of things that we can do to look at what's here. So one that will be important is that for a sphere, moment of inertia about its center is 2/5 mr squared. We've essentially got a bowling ball that is going to be, so we've got a velocity, we know an angular velocity. We'll have weight. Because of the way this is rotating, velocity is going to tend to be to the right, which means our friction force is going to be to the left. And we've got n. And so that's going to give us an I alpha in the opposite direction of the current rotation, and an m a sub g also opposing our current velocity. So you're looking for essentially knowing that this is kind of where we're starting. When will the ball start to roll without sliding? So essentially, at what point does velocity at the point in contact with ground, when does that velocity become 0? Okay. Any questions at this point? Okay. I'm working on getting that exam graded. It's close. It's just not quite done yet. I'll get those to you probably in the next day or so. I'm also going to go ahead and assign some homework since we haven't had any in a bit. And other than that, yeah, I think that's what we've got. We're going to try and get through momentum and then work and energy as well in the next couple of weeks. But in the meantime, have a great Thanksgiving. I'll stick around for a couple minutes.
Yeah. Is the statics project still due at 11:59 tonight?
Yes.
Okay.
Yep. Statics project due tonight.
And then do we have statics homework this Saturday or Friday?
It won't be due this week. It'll probably, let's see, it'll probably be due early next week,
Okay.
just to give you a little bit of time.
Yeah. All right. Sounds good.
Mm-hmm. Okay. I will stick around for a little bit, but otherwise have a great Thanksgiving.